Imagine standing beneath a vast night sky, gazing up at countless stars twinkling like tiny beacons of possibility. Now, picture setting your sights on one of those distant lights, a star system so far away that it takes over 4 years for its light to even reach us. That star is Proxima Centauri, our closest neighbor in the endless expanse of the universe, and a tantalizing target for humanity's most ambitious endeavor, yet our first interstellar mission. Scientists believe that within this distant system lies the potential for habitable planets, perhaps even a second Earth. But how long would it actually take to reach such a far-off destination? What groundbreaking technologies would we need, and what challenges would we have to overcome on this cosmic journey? In this video, we are diving headfirst into the science, the futuristic propulsion systems, and the mind-bending hurdles of interstellar travel. Get ready to discover how humanity could turn science fiction into reality and explore what it truly takes to venture beyond our solar system. Now turning to the astonishing distance to Proxima Centauri, let us first grasp the sheer enormity of this journey. Proxima Centauri is located approximately 4¼ light years from Earth. To put that into perspective, a single light year is the distance light travels in 1 Earth year, and light moves at an incredible speed of nearly 300,000 kilometers per second. Over the span of 4¼ years, that totals a staggering distance of roughly 40 trillion kilometers, or about 25 trillion miles. These numbers are so vast they can be difficult to comprehend, so let us break it down further. The distance between Earth and our Moon is about 384,000 kilometers, meaning you would have to make the same trip over 100 million times to cover the distance to Proxima Centauri. Even the distance to our Sun, a comparatively close 150 million kilometers, pales in comparison to this interstellar trek. Imagine if you were traveling at the speed of a modern jet, which is about 900 kilometers per hour. It would take you over 5 million years to reach Proxima Centauri. This extraordinary distance presents one of the greatest challenges humanity has ever faced, requiring entirely new technologies and engineering breakthroughs to even consider embarking on such a voyage. Yet, despite the difficulty, this immense challenge also inspires us to push the boundaries of what is possible and unlock the secrets of the cosmos. Moving forward, let us examine the current speeds of human spacecraft and the stark reality they reveal about the challenge of reaching Proxima Centauri. Among the fastest spacecraft ever built, the Parker Solar Probe holds the record, traveling at an astonishing speed of over 700,000 kilometers per hour. By comparison, the New Horizons spacecraft, which flew past Pluto, achieved a remarkable speed of over 58,000 kilometers per hour. While these numbers are impressive within the context of our solar system, they pale in comparison to the distances required for interstellar travel. To put this in perspective, even at the Parker Solar Probe's record-setting speed, it would still take over 6,000 years to travel to Proxima Centauri. At the speed of New Horizons, the journey would stretch to a mind-boggling 78,000 years. These figures highlight just how slow humanity's current spacecraft are when confronted with the vastness of interstellar distances. Even the fastest technologies we have today remain woefully inadequate for reaching another star within a single lifetime. This glaring limitation underscores the urgent need for groundbreaking advancements in propulsion technology. To make interstellar travel feasible, we must explore entirely new methods of propulsion that can multiply current speeds many times over. This need for innovation drives researchers and engineers to envision revolutionary solutions that could one day bridge the immense gap between stars. With this challenge in mind, we can now turn our attention to the exciting possibilities of breakthrough propulsion technologies that may one day make this dream a reality. Now turning to the possibilities of breakthrough propulsion technologies, we step into a realm of innovation that could dramatically shorten the travel time to Proxima Centauri. Among the most promising concepts is ion propulsion, which generates thrust by accelerating charged particles, or ions, through an electric field. While this technology is already used in some modern spacecraft for efficient, long-duration missions within our solar system, its thrust is relatively low, limiting its potential for interstellar travel unless significantly advanced. Another exciting concept is nuclear fusion propulsion, which aims to harness the same energy source that powers the Sun. By fusing atomic nuclei to release immense amounts of energy, a spacecraft could achieve much higher speeds compared to conventional propulsion. However, this approach remains largely theoretical, as the technical challenges of creating a controlled fusion reaction in a spacecraft are immense. Taking an even bolder leap, antimatter engines propose using collisions between matter and antimatter to produce energy with unparalleled efficiency. A single gram of antimatter reacting with matter could release as much energy as several thousand tons of chemical rocket fuel, potentially enabling speeds that approach a significant fraction of the speed of light. Yet, the production, storage, and handling of antimatter are monumental hurdles that have yet to be resolved. Among these groundbreaking ideas, one initiative stands out in its practicality and current development: Breakthrough Starshot. This ambitious project envisions sending tiny spacecraft called nanocraft, each weighing only a few grams, equipped with light sails. These sails would be propelled by powerful lasers fired from Earth, pushing the nanocraft to speeds of up to 20% of the speed of light. At this velocity, the journey to Proxima Centauri could be reduced to just over 20 years. While the idea is awe-inspiring, even Breakthrough Starshot faces challenges, from precisely aiming the lasers to ensuring the durability of these lightweight probes in interstellar space. Despite the remarkable potential of these technologies, it is clear that the time frame for a mission to Proxima Centauri would remain substantial, even under the most optimistic scenarios. This underscores the monumental task of overcoming the barriers of physics and engineering to turn humanity's dream of visiting another star into a reality. With the next phase of the journey in sight, let us delve into the critical role of cryosleep and life support in overcoming the challenges of interstellar travel. Decades-long missions to a destination as distant as Proxima Centauri demand innovative solutions to sustain a crew or even a payload over such an extended period. One fascinating concept is cryosleep, also known as stasis chambers, which aims to reduce the metabolic requirements of human travelers by inducing a state of suspended animation. This idea, often seen in science fiction, is now the focus of serious scientific inquiry. By minimizing the body's need for food, water, and oxygen, cryosleep could potentially simplify life support needs while also helping to mitigate the psychological toll of long-term isolation in deep space. However, developing this technology for practical use poses significant medical and engineering challenges, such as ensuring safe entry into and recovery from such a state, as well as maintaining the body's health over potentially decades of inactivity. For missions that forego cryosleep, life support systems must address the constant demand for essentials like oxygen, food, water, and waste management. Current technologies would need to be exponentially scaled and adapted for efficiency. Recycling systems that process and repurpose resources will be vital, given the impossibility of resupply missions over interstellar distances. Solutions might include advanced hydroponics for growing food, water purification systems that recycle every drop, and closed-loop oxygen generation systems. These technologies must also be designed for reliability, as a failure in any life support component could have catastrophic consequences so far from Earth. An additional layer of complexity arises when deciding whether to send humans or unmanned probes first. Sending probes avoids the enormous requirements of life support altogether, allowing for smaller, lighter, and faster spacecraft. These unmanned missions could gather critical data on the Proxima Centauri system, including its planet's environment and hazards, paving the way for a future human mission. On the other hand, sending humans would be a monumental milestone in history, embodying the spirit of exploration that defines our species. Yet, the risks, costs, and technical demands of manned missions are far greater. Should humanity prioritize robotic exploration to ensure safety and gather knowledge, or take the leap with human travelers to inspire and lead the way? These are questions that scientists, engineers, and policymakers must grapple with as we inch closer to making interstellar travel a reality. Moving forward, as we continue unraveling the intricacies of this cosmic journey, we must also consider the immense challenge of navigating vast and perilous interstellar space. Moving forward, the immense task of navigating through interstellar space presents an entirely new set of challenges. Unlike a straightforward trip across the solar system, a mission to Proxima Centauri involves aiming for a moving target over an astonishingly vast distance. Proxima Centauri, like our Sun and other stars, is not stationary. It is traveling through the galaxy at remarkable speeds. This means that precise calculations must account for the star system's movement relative to our own, ensuring that the spacecraft arrives at its destination rather than drifting into the endless void of space. To achieve this level of precision, advanced navigation tools and technologies will be indispensable. Autonomous systems equipped with artificial intelligence will play a crucial role in making real-time adjustments, as communication delays between the spacecraft and Earth would be too significant to rely on direct human intervention. These systems would use inputs from onboard sensors to detect and correct any deviations in the spacecraft's trajectory. Additionally, external references like the positions of stars could act as celestial signposts, guiding the spacecraft across the expansive interstellar domain. However, navigation is not merely a matter of plotting a course. The journey is fraught with potential hazards. Cosmic radiation, a high-energy particle bombardment from deep space, poses a serious threat to both the spacecraft's electronic systems and any potential human travelers. Shielding against this radiation will be a critical design consideration, as prolonged exposure could cause irreversible damage. Another significant danger comes from micrometeoroids, which are tiny, fast-moving particles that may seem insignificant but could cause catastrophic damage when traveling at such high speeds. Protective measures such as reinforced shielding or even active detection and evasion systems might need to be developed to safeguard the spacecraft on its decades-long voyage. These challenges highlight the immense complexity of navigating the cosmic seas, requiring a seamless blend of precision, innovation, and resilience. As we ponder these obstacles, another fascinating aspect emerges: the implications of traveling at extraordinary speeds and how it intertwines with the enigmatic nature of time itself. With the next phase of the journey in sight, we venture into one of the most intriguing and mind-bending aspects of interstellar travel: the implications of relativity. At speeds approaching a significant fraction of the speed of light, a phenomenon known as time dilation, predicted by Einstein's theory of relativity, comes into play. But what does this mean for a mission to Proxima Centauri? Simply put, time would pass differently for the travelers aboard the spacecraft compared to people on Earth. Imagine this: if the spacecraft were able to travel at nearly half the speed of light, a journey that might take over 8 years from Earth's perspective could feel much shorter to those on board, perhaps only a few years depending on the exact speed. This could significantly influence mission planning because, for the crew, the perceived duration of the mission would be dramatically shorter than the actual time elapsed. However, this does not change the fact that for everyone on Earth, including mission controllers, the spacecraft would still take the full expected time to reach its destination. While this effect is fascinating, it also adds challenges to communication and coordination. For example, if a 4-year message delay already exists due to the vast distance, the additional differences in time perception between Earth and the spacecraft could further complicate updates and interactions. This concept, though complex, truly illustrates the profound effects of traveling at extraordinary speeds, providing yet another layer of complexity, but also wonder to the dream of interstellar exploration. As we unravel these implications of relativity, we also come closer to understanding why Proxima Centauri and its planets present such an irresistible target for our first leap beyond the solar system. Now turning to the Proxima Centauri system, let us explore what makes this enigmatic star system so captivating, especially its potentially habitable planet, Proxima b. Proxima Centauri is part of a trio of stars known as the Alpha Centauri system, and at just over 4 light-years away, it stands as our closest stellar neighbor. Orbiting within Proxima Centauri's habitable zone is Proxima b, a planet that has sparked immense interest and curiosity among scientists. The habitable zone refers to the region around a star where conditions might allow liquid water to exist on a planet's surface, a key ingredient for life as we know it. Proxima b is particularly intriguing because it is slightly larger than Earth and orbits its parent star at a distance where temperatures might support the presence of water. However, this potential for habitability comes with its share of challenges. Proxima Centauri is a red dwarf star, much cooler and dimmer than our Sun, but it is also extremely active, emitting intense stellar flares. These flares release bursts of radiation that could strip away a planet's atmosphere over time, making it harder for life to thrive. Despite these obstacles, the possibility remains that Proxima b may harbor conditions suitable for life, perhaps under a protective atmosphere or even beneath its surface. What makes this planet even more fascinating is how it fuels humanity's timeless quest to answer one of the most profound questions: are we alone in the universe? By studying Proxima b, we not only inch closer to uncovering whether life exists beyond Earth, but also gain insights into the resilience of planets and ecosystems under extreme conditions. This quest to explore Proxima Centauri's planets ties deeply into humanity's broader journey of discovery, inspiring scientists, engineers, and dreamers alike. The allure of exploring a planet within the habitable zone of another star makes Proxima b a compelling target, not just for its scientific potential but for what it represents, a bold step toward understanding our place in the immense and mysterious cosmos. Now turning to the debate of unmanned probes versus manned missions, it becomes clear that each approach presents unique advantages and challenges. Unmanned probes have the significant benefit of simplicity when compared to the complexities of sustaining human life on an interstellar journey. Without the need for life support systems, oxygen, food, or water, these probes can be made smaller, lighter, and faster. This allows them to take advantage of advanced propulsion technologies and potentially reduce travel times significantly. Additionally, unmanned missions carry fewer risks as no human lives are directly at stake. They can endure harsh conditions, intense radiation, and long durations without the psychological challenges that human travelers would face. This makes them an ideal candidate for gathering preliminary data about the Proxima Centauri system and its potential habitability. On the other hand, sending humans to Proxima Centauri represents the pinnacle of ambition in space exploration, but it also comes with immense challenges. Such a mission would likely take decades, requiring advanced life support systems capable of recycling resources efficiently for extended periods. The psychological toll of isolation and confinement in deep space for years or even generations could pose significant mental health risks to the crew. Prolonged exposure to cosmic radiation presents another serious health concern, as does the physical wear and tear on the human body in a low-gravity or microgravity environment. Beyond these hurdles, manned missions also involve considerably higher costs and technical complexity, making them less feasible in the near term. The decision between these two approaches ultimately boils down to a careful balancing of priorities. Unmanned probes may pave the way for human exploration by providing critical data on Proxima Centauri and its planets. helping scientists determine whether conditions are suitable for future human missions. However, the allure of reaching another star system with human explorers embodies the spirit of discovery and innovation, capturing the imagination and inspiring generations to come. Whether humanity opts for an unmanned precursor mission, a bold manned journey, or a combination of both, the choice will shape not only the mission's success but also our understanding of what it means to explore the cosmos. As we weigh these options, it becomes evident that the path humanity chooses will reflect the balance between pragmatism and aspiration, setting the stage for a new era of interstellar exploration. With the next phase of the journey in sight, let's turn our attention to the mission timeline in real terms, a crucial factor in understanding the feasibility of reaching Proxima Centauri. Using current technology, such as the propulsion systems powering spacecraft today, the journey would be unimaginably long. For example, even our fastest spacecraft to date, like the Parker Solar Probe, would take tens of thousands of years to cover the immense distance of over 40 trillion kilometers. This staggering time frame highlights the need for revolutionary advancements in propulsion technology to make the mission viable within a human lifetime. Now consider the potential of advanced propulsion systems which could drastically reshape this timeline. Concepts like the Breakthrough Starshot initiative propose using nanocraft equipped with light sails, pushed by powerful lasers to reach up to 20% of the speed of light. At this velocity, a mission to Proxima Centauri could theoretically take just over 20 years. Similarly, nuclear fusion propulsion, though still in the experimental stages, offers another promising avenue with estimated travel times ranging between 20 to 50 years depending on its efficiency. These timelines, while significantly shorter than those possible with current technology, still span multiple decades, raising the question of how humanity can sustain interest and support for such a long-term project. To keep the momentum alive, milestones along the way would be essential. Sharing regular updates on technological breakthroughs, testing phases, and early mission results could capture public imagination and maintain enthusiasm. Additionally, fostering international collaboration would help distribute costs, resources, and expertise, providing a shared sense of ownership over the mission's success. Public engagement would also play a critical role, tapping into humanity's inherent curiosity and drive to explore the unknown. Whether through captivating media campaigns, interactive educational content, or opportunities for the global community to contribute to the mission's progress, keeping the public invested would be as important as the technological advancements themselves. As we evaluate these timelines and their implications, one thing becomes clear: while the journey to Proxima Centauri may take decades, the impact of such an endeavor would stretch far beyond the travel time, inspiring generations and leaving a lasting legacy for humanity. Moving forward, we'll explore yet another significant aspect of this mission: the challenges of communication over such an extraordinary distance. As the next challenge unfolds, let's consider the immense difficulties of communication during a mission to Proxima Centauri. At a distance of over 40 trillion kilometers, the time required for a signal to travel between Earth and the spacecraft becomes a significant hurdle. Since information is limited by the speed of light, it would take more than 4 years for a one-way signal to reach Proxima Centauri, and over 8 years for a message and its reply to complete a round trip. This delay makes real-time communication impossible, creating a need for breakthroughs in how we manage and interpret data from such distances. To tackle this, the spacecraft would need to be equipped with highly advanced autonomous systems capable of making critical decisions without waiting for guidance from mission control back on Earth. These systems would have to handle everything from course adjustments to identifying and reacting to unforeseen hazards, ensuring the mission's safety and success even in the absence of immediate human intervention. Moreover, this communication lag would profoundly affect how we troubleshoot problems or receive updates. engineers on Earth would need to anticipate potential issues well in advance, programming the spacecraft to resolve them independently. Additionally, data transmission itself would be a challenge, compressing immense amounts of information into manageable packets while ensuring minimal loss during transit over such a vast distance would require innovative solutions. Despite these hurdles, overcoming the barriers of communication would represent a monumental step forward, showcasing humanity's ability to adapt and innovate in pursuit of interstellar exploration. Up next, we'll delve into the fascinating details of the Proxima Centauri system itself, including Proxima b, a planet that has captured the imagination of scientists worldwide. As we draw this journey to a close, let's reflect on the incredible scope of what a mission to Proxima Centauri entails. The sheer distance of over 40 trillion kilometers, coupled with the limitations of current space travel speeds, highlights the immense challenge of reaching our nearest stellar neighbor. Yet, emerging propulsion technologies, from nuclear fusion engines to the innovative breakthrough Starshot initiative, offer a glimpse of hope by potentially reducing travel times to a few decades rather than millennia. Life support and cryosleep systems promise solutions for sustaining human travelers over such a long voyage, while autonomous decision-making systems and precise navigation tools underscore the complexity of interstellar travel. The challenges we face are monumental, but they pale in comparison to the rewards of exploring Proxima Centauri and its fascinating planetary system, particularly Proxima b. This journey would not only be a technological feat, but also a testament to humanity's unyielding curiosity and drive to push boundaries. Imagine the moment we receive the first images or data from another star system, or perhaps even discover signs of life events that would redefine our place in the universe. The first mission to Proxima Centauri represents more than just a scientific endeavor. It is a symbol of our enduring spirit of exploration and innovation. As we stand on the brink of this unprecedented chapter in human history, we invite you to share your thoughts. What breakthroughs do you think will make interstellar travel a reality? Let us know in the comments, and don't forget to like the video, subscribe to the channel, and hit the notification bell to join us on this exciting journey of discovery. The universe awaits, and together we are reaching for the stars.